All. This is Dr. A. Anuja, Assistant Professor, Department of Mathematics, Arulmigu Palani Andavar, Arts College for Women, Palani. In this lecture, we are going to discuss about equilibrium of body on a rough inclined plane under a force parallel to the plane. So, in this topic, we are going to see about one theorem. The statement of the theorem: a body is at rest on a rough plane. It's inclined to the horizon at an angle greater than the angle of friction, and it's acted upon by a force and parallel to the plane and along the line of greatest slope. So, to find the limits between which the force must lie. Now, let alpha be the inclinations of the plane to the horizon, and W the weight of the body, and R the normal reactions. So in this theorem we are splitting into two cases. So for the case 1 we'll take a figure 5, and for the case 2 we'll take figure 6. So in case 1 we have to refer the figure 5. So let the body be on the point of moving down the plane. So already we know that if the object moving on the downwards, so obviously the friction moving on the upwards, so both are in opposite directions. For this the body be on the point of the moving down the plane, so the limiting frictions acts up the plane. So here the limiting friction denoted as mu r. Let P be the force required to keep the body at rest. So the forces along and perpendicular to the plane will get P into cos theta plus mu r is equal to W sin alpha. So this is equation 1, and for sin, P sin theta plus r is equal to W cos alpha. This is equation number 2. Now we substituting the value of r from 2 in 1, which means we'll take the equation 2. What is equation 2? P sin theta plus r is equal to W cos alpha. So we'll keep r as on left side, remaining are take it into the right side. So r is equal to W cos alpha minus P sin alpha. So this is the value for the r. We substituting this r values into the equation 1. So the equation 1 becomes P cos theta plus mu. For this r we are substituting W cos alpha minus P sin alpha equal to W sin alpha. So therefore we'll multiply the mu with the term mu into W cos alpha minus mu into P sin alpha. So from left side we are taking P as a common. So P cos theta and mu P sin theta. So we are taking P as a common for these two terms. So it becomes P of cos theta minus mu sin theta. And next the mu W cos alpha, which is in the left side, we'll take it in this in the right side. So now we'll take W as a common, so we'll get W of sin alpha minus mu cos alpha. Now the equation becomes P of cos theta minus mu sin theta equal to W sin alpha minus mu cos alpha. So we'll keep P, we want P only, so therefore we'll take cos theta minus mu sin theta as on right side. So P is equal to W sin alpha minus mu cos alpha divided by cos theta minus mu sin theta. If the lambda is the angle of friction, suppose we know that the coefficient of friction, which is equal to tangent to the angle of friction, it's nothing but mu is equal to tan lambda. So we are replacing this mu as an tan lambda into the P value. So P becomes P is equal to W of sin alpha minus mu alpha, will substitute tan lambda into cos alpha divided by cos theta minus tan lambda into sin theta. Now we expanding this, we are substituting tan lambda what is the form of the tan theta is equal to sin theta divided by cos theta. Here tan lambda is equal to sin lambda divided by cos lambda, and taking into the LCM, so the P becomes P sin alpha W into sin alpha cos lambda minus sin lambda cos alpha divided by cos theta cos lambda minus sin lambda sin theta. So these are the form of sin A minus B and cos A plus B. So we are rewriting this. So W of sin alpha minus lambda divided by cos theta plus lambda. So let this value of be P1. So we are replacing P as in P1. So the P1 is W sin of alpha minus lambda divided by cos of theta plus lambda. So this is equation number 3 for the case 1. Next, the case 2. So we have to refer the figure 6. The body is just on the point of moving up the plane. So obviously the limiting friction down to the plane. So the limiting friction mu r acts downwards. So resolving the forces as before, we'll write P cos theta minus mu r is equal to W sin alpha. So mark it as equation number 4. And P sin theta plus r is equal to W cos alpha. This is equation number 5. Now in equation 5, we'll take r. So we take P sin theta into the right side. So r is equal to W cos alpha minus P sin alpha. So this r value we have to substitute in the equation 4. So the equation 4 becomes P cos theta minus mu of W cos alpha minus P sin theta equal to W sin alpha. So we'll multiple mu with the term, and we are splitting into the P term and the W term. So we'll keep P terms are on the left and W's are on the right side. So we'll get P of cos theta plus mu sin theta equal to W of sin alpha plus mu cos alpha. So therefore we need only P. So we'll take remaining terms into the right side. So the P becomes W sin alpha plus mu cos alpha divided by cos theta plus mu sin theta. So we are replacing mu as in tan alpha, and we are again substituting tan lambda as in sin theta divided by cos theta, and again we'll take the LCM. We'll get W sin alpha cos lambda plus sin lambda cos alpha divided by cos theta cos lambda plus sin lambda sin theta is equal to, we are applying this form, we using the formula sin A plus B and cos A minus B. So therefore the P becomes W sin of alpha plus lambda divided by cos of theta minus lambda. So we are taking this P as in P2. So the P becomes, for the case 2, P2 equal to W sin of alpha plus lambda divided by cos of theta minus lambda. This is equation number 6. So from this P, forces P1 and P2 are limiting values for the force P. So necessary to keep the body in equilibrium. So if the P lies between the forces P1 and P2, the body will remain in equilibrium. So the notes are, the value of P2 may be obtained from that of P1 by changing the sign of mu. Similarly, if we putting theta as a 0, the result gives a previous one. So the corollary, when can find the directions and magnitude of the least forces required to drag the body up to the inclined plane. So the P becomes, for the K, from the P is taken into the from case 2. So which means P is equal to W sin of alpha plus lambda divided by cos of theta minus lambda. Since alpha, W, lambda are the constant things. So if P is least, if cos theta minus lambda is greatest. So therefore, if cos theta minus lambda, if cos theta minus lambda is equal to 1, and when theta minus lambda is equal to 0. So if this is equal to 0 means we equating these two, we'll get theta is equal to lambda. Now substitute in this value and we'll get the value of P is equal to W sin alpha plus lambda. So from these two cases, the force required to move the body up the plane will be least when it's applied into direction making with the inclined plane an angle it's equal to the angle of friction. So this result sometimes stated as the best angle of traction of a rough inclined plane is the angle of friction. Hence proved. Thank you.